Next speaker, Łukasz Michalak. You're welcome, Dr. Łukasz.
Thank you very much. So the title of my talk is Framed Cobordism of Systems of Submanifolds in the Classification of Free Quotients. And this talk is based on the joint work with Wacław Marzantowicz. And my aim is to show how systems of submanifolds of codimension 1 and a framed cobordism can be used to describe epimorphisms onto free groups and the structure of their set. In particular, I will show a nice proof of a classical result of Grigorchuk-Kurchanov-Zieschang about equivalence of epimorphism for surface groups. So first, let us fix a copy of a free group of rank R as the fundamental group of the bouquet of circles. So the wedge product of circles. And the first notion related to free quotients is the Corank of the group, which is the maximal rank of a free group onto which there is an epimorphism from the group. And this is well defined. G is finitely generated, and it is of course not greater than the rank of integers of its abelianization. And if this is the fundamental group, for example, of a closed manifold M, then the Corank is bounded by the first Betty number of M. And for example, classical computations for surfaces show that this bound is attained for a closed orientable surface sigma G of genus G, and the Corank here is G. But for non-orientable surface of genus G, the Corank is the floor of G over 2, while the first Betty number is G minus 1. And shortly, if sigma is a closed surface of Euler characteristic minus k, then its Corank is the floor of k over 2. Note also the basic properties of Corank. It is additive with respect to the free product of groups, and the Corank of the direct product of groups is the maximum of the Coranks. In the study of epimorphism, we consider the notions of equivalence and strong equivalence of homomorphism phi and psi between groups. And clearly, strongly equivalent epimorphisms are equivalent. And let us take the classical result of Grigorchuk-Kurchanov-Zieschang. If sigma is a closed surface of Euler characteristic 2 minus k, and R is the number between 1 and the Corank, then there are two finite numbers, P and Q, of equivalence and strong equivalence classes of epimorphism from phi 1 of sigma to FR. And if sigma is orientable or non-orientable of odd genus, then P and Q are equal to 1. But if the surface is non-orientable of even genus to M, and if R is not maximal, so it is smaller than M, then P is 2 and Q is 2 to the power R. But if R is maximal equal to M, then these numbers are decreased. Okay, so I will only briefly mention about the following machinery which allows to describe the structure of the set of homomorphism from G to the free group FR. And it is the so-called Makanin-Razborov diagram. They were created in the context of solving system of equations in the free groups. And for a finitely generated group G and the free group FR, it is a finite diagram of groups which arrows are proper quotients, and the groups occurring in the diagram are limit groups. And at the end of all paths in the down, there are free groups. And for this data, any homomorphism can be factorized through such a path in the down with possible composition with modular automorphism of groups in the diagrams. In particular, for surface groups, the paths in Makanin-Razborov diagram have length 1, and we obtain the previous notion of equivalence of homomorphism. So now let us go to more geometric objects. We define a system of hypersurfaces in the manifold W, compact manifold possibly with boundary, as a sequence of disjoint, properly embedded, and two-sided submanifolds together with their framings. We have tubular neighborhoods, which are product neighborhoods, which we denote by P of Ni. And we also use the following denotation on the complement of the system. And first of all, we define the homomorphism into free group induced by the system, which is just an extension of Pontryagin-Thom construction. And the homomorphism phi n is induced on fundamental groups by MFFn from W to the bouquet of circles. And Fn is defined as follows. It maps the point xt in the tubular neighborhood of Ni into T on I circle, which is considered as the quotient of the interval, and the complement of the system, Fn maps to the base point. And we say that two such systems of the same size in the closed manifold are framed cobordant if there are R disjoint framed cobordis between corresponding submanifolds. It is equivalent to the case when the induced homomorphisms are equal. And also denote by omega FR1R of M, the set of all framed cobordis classes of systems of hypersurfaces of size R in M. Here is the set of base point preserving homotopy classes of base point preserving maps from M to the bouquet of circles, and we have the following bijections of this set. So the bordis class of N is mapped onto the map Fn, and it is sent to the induced homomorphism. And here we have bijection, since the bouquet of circles is an Algebraic plane space. And here we need to smooth this function outside the inverse image of the base point. And we take regular values, and their preimages form the desired systems of hypersurface. A system is called independent if its complement is connected, and it is regular if all submanifolds are connected. And independent systems induce epimorphism. So the question was whether the converse is true. And in fact, any epimorphism from onto the free group is induced by a regular and independent system of hypersurfaces. And the idea of the proof is the following. First, we take any system which induces phi. And then if there is a path gamma which joins two connected components, A and B, of the some submanifolds Ni, which omits the rest of the system, and which joins these components from the same sides determined by the framings, then we perform the connected sum of A and B along gamma to produce one connected submanifold. And if we substitute A and B by their connected sum in the system, the induced homomorphism does not change. And we repeat this procedure as long as we can, obtaining a new system, which has the property that for any I, there is a unique connected component, Ci of Ni prime. For it, there is a loop which intersects the system only in Ci, and which is mapped by phi to the I generator of F. And these submanifolds Ci form the desired system, which is regular independent and which induces phi. So by HFR R of M, we denote the set of all framed cobordis classes of regular independent systems of hypersurfaces of size R in M. And as a subset of omega FR, it corresponds in the home set bijectively to the set of all epimorphisms from phi 1 of M to FR. And we use the following denotation on the set of self-diffeomorphisms of M, which preserve the base point. The orbit is of this action on classes of independent systems of surfaces subjects onto strong equivalence classes of epimorphism onto free groups. In particular, for surfaces, we have the Nielsen theorem, which states that any automorphism of the fundamental group is induced by some homeomorphism of the surface, and we obtain here one-to-one correspondence. And this is a geometric way to describe strong equivalence classes. Now, let us start the proof of Grigorchuk-Kurchanov-Zieschang theorem. First for closed orientable surface of genus G. And note that regular independent systems of submanifolds of size R in a surface consist of just R circles. In orientable case, complements of any two such systems are always diffeomorphic to the same orientable surface with 2 R boundary components. So we may take a diffeomorphism H bar between their complements. And by homogeneity, we may require that it maps boundary components from one system to the boundary components which correspond from the second system. And next, we glue a lower basis of cylinders, P of Ni and P of Ni prime, to the complements as they were cut off. And we obtain gluing maps, Gi and Gi prime, between other boundary components, which lead back to the sigma G. And we extend H bar to the diffeomorphism H prime. And now H prime can be induces a self-diffeomorphism H of sigma G after gluing operations via Gi and Gi prime, even only if corresponding gluing maps are isotopic. It means that this composition, so we start here and go here, next here, and then we come back here, is isotopic to this gluing map. And because here we have orientable surfaces, all gluing maps are orientation preserving, and this condition is always satisfied. So we obtain a diffeomorphism H, which maps a first system to the second one. Thus, we have only one orbit of the action of D on this set, and there is a unique strong equivalence class of epimorphisms. And the similar situation is for non-orientable surface of odd genus. That here the complement is always non-orientable surface with 2 R boundary components. So we have H prime as before. And now also we can always construct H, a self-diffeomorphism of the surface, because we may compose H prime with a self-diffeomorphism which is identity on all boundary components except one, on which it is orientation reversing. Then this condition, these two maps are always isotopic, and also we obtain a unique element in this set. So let us summarize. We have these two cases, and the P is always not greater than Q. And we need to prove the following values for non-orientable surface of even genus to M. And now the complement can be orientable or non-orientable. We define the following family of regular independent systems, Nj, for any non-empty subset of J of integers from 1 to R. And Nj is a system of size R such that its complement is orientable, and gluing maps are orientation reversing only for indices from this set J. And moreover, if R is smaller than M, is not maximal, we take a system N0 whose complement is non-orientable, but the system does not exist for R equal to M. And the crucial fact, which was not straightforward for us, is the following proposition. If we have two systems of hypersurfaces, independent and regular, such that one complement is orientable, but the second one is non-orientable, then they are not frame cobordant. And using this fact, we show that all systems nj and n0 are not frame cobordant to each other, and there are different elements in this set. So we have the following numbers of strong equivalence classes of epimorphism in this case. And to complete the proof of Grigorchuk-Kurchanov-Zieschang theorem, we have to go to equivalence classes. So we need to geometrically represent automorphism of the free group. Recall that automorphism group of Fr is generated by elementary Nielsen transformation of the following two types for a basis A1AR, Ni inverse AI, and leaves fixed other elements of the basis. And the automorphism Nij replaces AI by AI times Aj for two different indices A and J. And we define analogs of these operations for an independent and regular system of hypersurfaces. The operation H1 only changes the framing of the submanifold Ni to the one with the opposite orientation. And the operation H2 transform a system N to Nij with replaced Nj by the connected sum of Nj with the parallel submanifolds to Ni. And the result of this operation on induced homomorphism is the same as the composition with the corresponding Nielsen automorphism. So in H2, we have Ni, a submanifold parallel P1 of Ni, which corresponds to Ni times 1 in the tubular neighborhood. And we take an arc gamma, which joins to Nj, which always exists since the system is independent. And we perform the connected sum as before. And for a new system, we only need to take smaller tubular neighborhoods. And this is to the following characterization. Two epimorphisms are equivalent if and only if one of the system can be transformed by using a finite number of operations H1 and H2 to a system which induce strongly equivalent epimorphisms to the first one. And therefore, for non-orientable surface S2M of even genus, we consider a subset J such that J is in J and I is outside J. And using the operation H2, the system Nj is transformed to the system which represents the same element as an I in this set. And it turns out that I is equal to J plus I. And so the operation H2 shows that all systems Nj induce equivalent epimorphism as this system. So yes, so all these epimorphisms are equivalent, and the systems N0 and Ny induce non-equivalent epimorphism because defined operations do not change the orientability of the complement. Therefore, we have two equivalence classes of epimorphisms if R is smaller than M and one for R equal to M. And maybe I finish in this moment. So thank you and sorry for the problems.